First of all, I want to thank the organizers for this very nice conference. It's a very nice place, very nice talks, very nice people. So everything is very nice, very awesome. And yeah, having the talk on the last day increases the pressure a bit because there were so many nice talks. Let's hope I can somehow convince you. So yeah, as Michael already teased, I will tell you a bit about flying domain walls in driven magnets, which I'm doing with my supervisor Achim Roche. Don't be that confused by the wings. Yeah, there will be no wings later. That's just art. But additionally, it's not just driven magnets, but we also call them like active magnets. And I try to convince you a bit about what this means. So let's first come from the perspective of active matter a bit. So I just stole some pictures here from a PhD thesis, just so that you see where it's from. So there's a flock of birds, a school of fish, or like humans walking around in Tokyo, and some cells. And all of these have something in common, which is these are all like single organisms, which then together have some collective behavior. So you have this emergent collective behavior in these active matter systems. So I mean, here in this flock of birds, you have all these birds flying. Like each of them is flying alone, but then together they build this flock, and then the whole flock moves together. Or like for the school of fish, it's even very important for them, like to survive, like to like hide from sharks or appear like a bigger fish in total. This might not be so important, but yeah, our question is now like, can we find similar in magnets? And yeah, as the title already teased, it might be the domain walls, but maybe it will still be surprising. So let's start from a more simple starting point, which is the XY model. So we have antiferromagnetic coupling in the XY plane. So this is this one-dimensional chain, and then they align antiferromagnetically in the ground state. This is the starting point, and now we kind of want to drive it. So we try to drive it with a weak field in Z direction. Like later we might do it a bit more prominently. And then we want to look what it expects, and sadly I have no video for this. But what happens is that you have some oscillations, but there's no net rotation activated. So I will later tell you a bit about what the goal of this rotation is. So in principle this means this is not so interesting. Like from symmetry reasons, it's kind of clear that there's not something happening. So we want to go to an additional step, which means that we additionally introduce this ferromagnetic coupling to this antiferromagnetic XY chain. And on top of this, we put this anisotropy. So I think this was already mentioned in the first talk of today. So you can have basically some kind of these. So it was a similar potential. And then for R smaller than 0, you actually get these two minima. So which means that the system wants to align with this ferromagnet because this anisotropy couples to the Z direction. So we either align like up or down in this direction, which gives us this little tilt. So much to this part. And then in addition, now we actually want to drive it again, right? I mean, this is supposed to be about driven magnets. So in addition to these two ingredients that we already have, we now introduce an oscillating magnetic field. And to actually activate the rotation, we need it also staggered, staggered in space, which means, And at the end of the day, what we get is some nice rotations. And here I now have some nice videos for you. And the interesting part here is that in the way we constructed it, it means that if the spins point down, they rotate clockwise, and if the spins point up, they rotate anti-clockwise. So there's some sort of, you could think of it as there might be some symmetry breaking, because depending on how the spins align up or down, you have the exact opposite rotation. So, and then in addition, if you would now do some perturbation theory, so you just take this micromagnetic model and then you expand, and average over time, you actually notice, I mean, you see the rotation already, but you will see that it's linear in time, which gives you this rotation, and you can also write it proportional to SZ, which is important later. And in this perturbation, you will notice that, so for weak fields, it's a second order effect in the driving field. And here you can also see again that it's important to have it staggered. So if we don't have it staggered, then we have the same coupling in space to the magnetic field, the effect is actually 0 again. Yeah. So what we have done here is basically we have activated this Goldstone mode, so the rotation in the XY plane. And just to repeat it again how this is, so here you have the video again, but so at first we have this SO3 symmetry, and then this anisotropy in Z direction breaks this down to a U1 symmetry in the XY plane, which is exactly then the Goldstone mode and the rotation, and the Z2 reflection along the Z direction, where you then either have clockwise or anti-clockwise rotation. And then, yeah, yet there's also no driven magnets yet, but just no active magnets, but only driven magnets, so in this order. And here, just to advertise Nina's thesis again, yeah, she did a lot of activation of Goldstone modes with various systems. For example, this Archimedean screw, which she can realize very, very small or very tiny compared to the ones you know. Yeah, so recommended. Then, yeah, what we actually do is we don't simulate this micromagnetic model, but a more coarse-grained model. So let me introduce that too. So the idea of that is that in a long wavelength limit, so you can also expand this and then see which terms you need, and then you write down the next, like the lowest order coupling terms. And what turns out, so we have some damping here. I already noticed that I'm a bit bad in notation because Gilbert damping is usually alpha that's driving here, and my damping is lambda. Please don't get confused by that. Yeah, then we have in both terms a diffusion term. The coupling term is actually realized only by this phi dot, which also realizes with this diffusion term basically like the next, the lowest order coupling term. Then we have some white noise here and the anisotropy on this term. And yeah, just to, I think this might be clear, but just to face it again, so if you want to have the spin and you have the magnetization in Z direction and the angle phi, which is the Goldstone mode, just to repeat it again, then you have your spin. And now we can come to the final question with this model. Okay, so what will happen to a domain wall now? Like we have this one state where they all rotate clockwise, and we have this other state where they all rotate anti-clockwise, and if we have the domain wall in the middle, yeah, what will it do? Yeah, and the question, of course, are they active, or will they just yeah, hang around? And for that, I also have a nice video. So the title already says it. So the domain wall flies through the system. So here's the domain wall. I hope it plays again, yeah. And you will see that on the one side, you see that they all rotate clockwise, and on the other side, they all rotate anti-clockwise. And when the domain wall comes, it basically changes this behavior and runs through the system. A different perspective on that could be this. So we just plot the two variables that we have, so mz and phi, and then we see, okay, they move through the system. Okay, phi is also increasing in addition. But that's just this linear increase that we had before. The more interesting fact is like this collective moving through the system, which is exactly this like emergent collective behavior that I've mentioned from the active matter before. But now we have this like rotating spins, which then collectively like transport this through the system. And then, yeah, we see this moving solution. And we can make this ansatz and plug it in our equations of motions and then do some math, but I will spare you with this. And we even also neglect this term. So we make it very simple. And then what we can find is that we have two velocities. Like, so there's also some symmetry breaking, like the domain wall can either go in one or the other direction. And it's dependent on alpha, which was the driving, not the damping. And we can also find this usual domain wall shape. As said, we neglected quite some terms here. It looks not too bad. There's deviation here exactly at these curves, which mostly comes from this term. So if you then go further in the orders, then you can get even better results. But I think it's already quite nice that on this level, and also the velocity is off by 6% or so from the estimated value, even though we neglect most higher order terms, which is quite nice. Yeah, so now we have done all this one domain wall, and it's moving, and it's great. But now we could actually think of several domain walls and see what happens then, or what will they do. So, yeah. It was actually a work in progress title, and then I didn't change it because I thought it's funny. Yeah, so what you actually see here is that, okay, the domain walls, they can move in one or the other direction, which means they don't collectively like go through the system, but they actually can annihilate each other and meet. Yeah.
No, but like their moves, so they have some kinetic energy, in some sense, some kinetic energy. So how can they do it? Because I would expect like a scattering.
Yeah, but I mean, you have this one rotation of the one side and the rotation from the other side, and then they start meeting, and you want this collective transition. So, and I think then, yeah, maybe scattering could be an option. I'm not entirely sure. Yeah, if you scatter, right? Right, thanks. Yeah, so yeah, the domain walls can annihilate each other if you start with several domain walls. So the next question could be, so this was all now at t equals 0, so you could now say, okay, now I want to be at finite temperature, so I add some noise to the system. And if I add noise to the system, noise naturally in one dimension, domain walls always survive, so you naturally create a several number of domain walls if you have noise. And then we can play this game like noise against drive, basically. So the drive kills the domain walls because you force them to meet faster, and the noise creates, oops, that was a bit too fast. And the noise creates the domain walls. And then we find this curve in some sense. So here it drops a bit. I would say something later to it again. So yeah, so we have this domain wall density against the drive. And then we actually see the behavior we expect. So the higher the drive is, the lower the density of domain walls is, because you force them to meet faster. The noise will create constantly the same, so we keep the noise the same. So the domain walls, there's a constant number of domain wall creation. And then you can make a short estimate of how it should look like, which then results in this plotted curve, which is quite fine in this area. But so the estimate goes as follows. That you say, okay, you have this domain wall density, and then you say, okay, this is like the average distance between the domain walls, and then you also say, okay, if two domain walls meet, this is like the average collision time, and then yeah, you can plug the density in there, and if you then use this equation on top, so you so I always made some simulations and then waited long enough that there's a stationary state. So the change in the domain wall on average is 0. And if you assume that and then plug it in, at the end of the day, you would get some alpha to the -1/4, which is exactly what I used for this fit here. And it fits quite nicely in this regime. One has to add that, of course, this just takes into account like two domain wall meetings, basically. So like no higher, like depending on how fast you make it, there might be several domain walls that meet. And also if you might have not enough domain walls anymore to play this game or something. So there's a limit to this.
So the noise is just thermal?
Yeah, the noise is just thermal noise and creates domain walls over time, and then we wash them out again with our driving field, but not all, depending on how strong it is. And then you could also ask, so I wrote a code to check if they are moving left and right. Because this, I mean, before we said, okay, there are some moving left, some moving right, and there are sometimes these games where you say, okay, one takes over, like one direction might take over. This is actually not the case. So as you can see here, like they are both, so the number of both, so the dashed lines are the right movers and the solid lines are the left movers. And you can see that the number of them is like approximately the same at all driving strength. So there's no favorite direction at the end of the day, and no symmetry breaking in that. And as a last teaser, like in addition, like 1D might be too boring, so we could also do this game in 2D, and then at first we do it without drive, so just the system itself, which is kind of like easing-like, and then you just see, okay, there are domain walls forming, and they slowly diffuse around, and once we turn on the drive, so they started exactly at the same initial state, you see that, okay, we actually like remove the domain walls in this case. And also here I want to advertise something. So there was a paper recently, it's now an archive, which gives a more field theory perspective on exactly such a model where they analyze the phase transition, which is then a first order phase transition, which we also would like to observe. This is what I'm currently working on. Yeah, so this is quite interesting. I mean, you see that the dynamical properties completely change if you turn on the drive, which is usually known for these active systems. And then, yeah. So, also recommended. And yeah, as last, a summary, I actually just put the pictures and videos so that you can see them again. So what have we done? We found some active matter or active magnets here, which are these moving domain walls in the system. We observed like many domain walls also, and at the end of the day, I also showed you how you can get rid of all the domain wall story in 2D by just turning on the drive. Yeah, and as last point, thank you for your attention.